Okay, well, thanks first of all for inviting me to speak. And I must apologize to all the previous speakers for not being there for your talks. I'm really sorry. But I can imagine, I mean, from this morning, seeing the talks in this morning were great. So it's a great conference. Okay, so I'll tell you about these three notions. And the idea of this talk is really to introduce you to these objects and to learn about them. So please interrupt me. Yeah, forget it, it's recorded, you know, or anything. Like, just ask me questions, and I'll be happy to explain. So let's start with graspers, actually. And those of you who were here last week already know about them. So let's start with this 4-ball, obviously. Okay. So this is the 4-ball in which I want to fix two arcs, U1 and U2. So U1 and U2 is an embedding of two disjoint arcs in D4. Okay? And the model grasper is just the complement of 1. So I'll just define G as D4 minus, say, U2. But actually, I want to take out a tubular neighborhood of it. And I don't want to worry about these tubular neighborhoods and framings and stuff. So I'll just write this, which just always will mean some tubular neighborhood, which is trivial. OK, so this is just the definition of this space. But then what we're going to consider in it is the following isotopy of the arc U1. So here is U1.
You take out both of them or only one?
Just one. So U2 is removed. I will not draw it removed, but just imagine it's removed. And the important thing to know about it when is that in this dimension 4, so in our D4, as I said, this tubular neighborhood will be just trivial. So this will just be a nice trivial D1 cross D3 in the neighborhood. So that means that if you fix a point in this D1, and you will have a normal 3-ball, and I want to remove the interior of that 3-ball and look at just the boundary. So this is the sphere that I will draw now. So this is a meridian sphere to this arc at this point. Okay, so this is just the analog of the meridian circle in dimension 3. And like, if I just didn't draw this, I'm trying to convey that this is higher dimensional, but if you forget about it, this would be just a circle that's a meridian at a point of this arc. Okay, and now I'm using that sphere, and I'll foliate it. Let me just do a bigger picture here of that sphere. So what I'm going to use is there is a foliation of the sphere by arcs, where I'll fix one arc here. And now just think of it as like it's very elastic. You can just move it, twirl it around the sphere. So it gets longer and longer. It stretches like this. And it covers the whole sphere and comes back. OK? OK? So this here is a 1-parameter family of arcs with fixed endpoints. So of arcs in S2, rel their endpoints, right? Now I'm going to use that here on this meridian sphere. So here is that arc, and just think of this whole family. I'll use it to make a non-trivial movement of the first arc. So arc U1 will start moving. So we'll have U1T is going to be an embedding of D1 into G. So we will at all times be in the complement of U2, such that U0 as U1 is just our U1. So we just start with this. The first part of the isotopy is with your finger, just push the arc close to the sphere. And then, OK, so let's just say the first moment it came here. So in some 0 to epsilon, you did this movement. Then it just connects, steps onto this. Then from 1/2 to, from 1/4 to 3/4, say you're just doing this motion, you go around, you come back where you were, and then you can just pull the finger back, okay? This starts with U1, finishes with U1, and I claim that's some non-trivial isotopy of the arc, okay? So we call it swirling isotopy. And now, as I said, this is just a model, okay? This is a model grasper. In the model grasper, I have an interesting movement of arcs, and now I can just plug it into any 4 manifold. So definition, first of all, fix an embedding C of S1 into X, a 4 manifold. Yeah, I forgot to say everything is smooth in this talk. So it means smooth embedding, smooth manifolds, and so on. So fix an arc, then a simple grasper. Well, relative to C, is an embedding. I'll denote it just maybe curly G. It's an embedding of this model grasper into G, into X, such that it intersects. So inside of G, I have U1. So if I take G of U1, it intersects C in one arc. Okay, so let me see my notes. It's just, G, the intersection of the whole grasper with C is just G of U1. So that's the only condition.
So what's C again?
Sorry? C is fixed. Fixed circle, yeah. And another condition is that I want G of this S2. So, this is a 2-sphere that I denote as S2 because this is my U2. G of S2 is a small meridian of C. I mean, it doesn't have to be small, but I mean, it bounds a 3-ball that intersects, this C in one point, small meridian of C. So just think of it, it's a small meridian. And then we have, so this is first part of the definition. Second part is, given such a thing, you can use this isotopy to construct an isotopy of circles, okay? So given G, the corresponding grasper family is just defined by, it's a family of GT of circles defined by GT I mean, it's a map, but yeah, let's just define it's like it's in the image. So you take your G, you take your C. I'm not going to have space. You take your C, and you remove this arc. How did I? Yeah, it's just remove G of U1 from it, and glue in G of U1T. Okay, so let me draw a picture. So we now have another thing in the game, and that's our circle, C. And now the only thing that we did, so this grasper is basically, you can think of it as a 4-ball, right? I'm embedding a 4-ball, but with this condition that U1 goes onto like a part here. So here is what G of U1 is. Okay? And somewhere else I have a meridian, which is this blue sphere. Okay? So Grasper will really be like a 4-ball that intersects here and here, something like this, where like this U2 is basically removed. So inside of this, now I'm doing this finger isotopy. The finger is coming closer to the sphere. So yeah, I'm describing the family GT of circles. You start with a red circle, and then you push with your finger more and more until you come close to the sphere, which is just a meridian of your circle somewhere else. You move once around, and you come back. Yes, so note that the G0 is G1 is C. And note that somehow, remark, this data is really determined by just a group element, okay? Grasper, simple Grasper. Is determined by a group element. Fundamental group element. What I mean by this is I already fixed two things, that U1 and U2 need to go here. So I just need to kind of, up to retracting this ball to like somehow its skeleton of what we're doing. We're just choosing basically an arc here that connects these two. So you can think of it, the Grasper is just a thickening of this. And then the only really choice that you have is this group, fundamental group element here. So maybe there is some loop G here. G is in pi 1 of x. That's really the only choice, right? You're just going from one point on your circle to another point. This determines this motion, okay? So let me tell you why this is useful. Why is this? Sorry. Okay. So this is useful, yes, because of the following theorem, which I'll attribute to Dax and Gabay. And then the case of circles was studied by myself. And that's that simple Graspers generate the following kernel. You go from pi 1 of embeddings of circles to x based at C. And then you can include this into immersions. So you go to pi 1 of immersions of S1 into X, based at C. So we have these two spaces. So here I'm thinking smooth embeddings of the circle into X, which has this usual Whitney-C infinity topology, which is just what you would expect. And then you're comparing embeddings to immersions. So these are only smooth maps with injective derivative, whereas those actually are also injective maps. And then it turns out that any one parameter family of immersions of circles, you can actually lift to embeddings. This map is surjective, but has some kernel. And the kernel is exactly generated by simple Graspers. So as an exercise, let's check that this is trivial in immersions. So let's check that it's really in the kernel of this map. So what I need to produce is for this one parameter family of embeddings, I want with another parameter to trivialize it in immersions. And then you can see, I hope, that because in immersions you're allowed to do double points, at some moment here, you have this arc on the one parameter family of arcs here, and you're really going around this sphere. But like in classical knots, you can do crossing changes. If you're allowed to do crossing changes, you can undo this because there is a ball, this sphere here, meridian sphere bounds the meridian ball. And then this gives you one parameter family that resolves this, takes it to the trivial family. So it is really in the kernel to emergence, and the claim is that it generates everything. And then you can wonder, okay, but what are the relations between these different things? And actually, this kernel is isomorphic to, well, you can take linear combinations of such graspers. In other words, you can concatenate things in pi1, right? I could first do simple grasper for G, then I do a simple grasper for G2, and so on. So there is a group structure on this. And actually, these things commute, turns out. So it doesn't matter whether you first did G1 and then G2. So this is this, but there are relations, and they are interesting. First of all, you will kill the group element 1. In other words, if here there's nothing, you can undo this. And this is an exercise, well, those who were here last week, it's easy. But it's really the same way that you would do it for knots. And then you also kill something more, and that's the little vex that depends on C and depends on pi3 of x minus a 4 ball. Well, okay, sorry. It's a bit more because I'm with circles. Did I make a mistake in my notes? Or yeah, okay, let me, not specify this. But let me just point out that there is a very interesting invariant that goes, so just a note, I'm not going to talk about it, but I find it very interesting that you, for this 4 manifold, you can cook up an invariant like this, that a priori is not, it's more than an algebraic thing. So it really uses the manifold X, and the first thing you need to do is represent this tree sphere by a 2-parameter family of immersed arcs, and then you're going to count double points of those arcs. So I just wanted to point out that this is something, I mean, I really find this interesting because it really depends on how your tree sphere lives in your manifold. And even if manifolds are homotope equivalent or homeomorphic, the way that you foliate by smooth arcs, smooth immersed arcs, it's not clear whether you're going to get the same thing. Well, it must not to me. Okay, are there questions about this? Okay, so this is a short summary of graspers. Yeah, one thing I wanted to say, I don't know why this is dying. Yes, yes.
So your model grasper, you talked about like actually cutting out a tubular neighborhood of U2.
Yeah.
So what's left is like a S2 cross.
Yeah. Yes.
And then when you define the grasper, you
Yeah.
talked about just embedding that piece.
Yes.
But it seems like in your picture, like you were saying, you want to have the whole 4 ball. Because, I mean, for example,
Yeah.
if you're actually just embedding like S2 cross E2, you could like run over some pi2.
Yes. No, very good question. And this is why these are called simple graspers. And that's because I had the second condition that I really wanted the blue sphere to be a little blue meridian of the red. So I restricted this embedding of S2 D2 to really be just, a neighborhood of a little meridian. And that's why I claim that this is completely determined by this group element. But I agree, and this is exactly the point, that you could do more complicated things. You can find interesting 2 spheres in your manifold and go and do the twirling isotopy around them. And many such things actually live here, right? If your 2 sphere is non-trivial in pi2, this is going to be visible here. It's visible in emergence that this class is non-trivial. But then you can do mixtures and who knows what. But the point is that you're never going to get anything like apart from this and that combined here somehow in this short exact sequence. So another thing that I didn't say is that this doesn't split. So there might be like non-trivial combinations of things that you can come up with, like combining a non-trivial two-sphere and a non-trivial simple grasper. Here inside, you can just kind of think of more complicated graspers.
Okay, so to get the whole D4, you would just like plug up the meridian sphere?
Yeah, you just need to choose a meridian sphere and then like a path to some other point. Because this is the only thing that's important for this twirling isotopy, right? How do you get from here to there? And this is determined by the group element, because we're in dimension 4, so there's not really much choice.
That makes sense.
Yeah, that's a good question, yeah. But actually, this brings me to another point. Why are these called graspers, and why do I give them a name at all, and so on? And this is because actually you can generalize this to graspers of higher degrees. So these are actually degree 1, but there exist graspers of degree n that give classes in pi n of embeddings. So higher homotopy groups of embedding spaces. And then the story is not that you want to compare to immersions. These graspers of degree n will generate certain kernels to something else. And this is related to embedding calculus, if you've heard about this. And this is something that I defined inspired by claspers that unfortunately I don't think I'll have time to talk much about. Maybe at the end I'll mention. This is claspers from classical dimension 3, classical knot theory, and also gropes, which is also in dimension version 4 dimension 3 of, so it's like claspers and gropes, and they also grasp this knot. So okay, so that's just a remark. And yeah, I wanted to give you one example. Pi 1 of embeddings of S1. Okay, so I'll now switch to framed for this example. So I'll write it like this. So like you can do a similar thing for like when you include framings, and then there are just some little Z2s that make a difference. It's difficult actually to compute in general, but okay. Here we are based at some framed C. Yeah, and this is going to be isomorphic to Z times Z mod 2 times Z infinity. This Z comes from the family of circles, which just rotates the circle. So you just rotate it as time passes. This Z mod 2 is just the framing. You can just rotate all the normal disks. And it's going to be, because it's 3 balls, it's just going to be order 2. So this is rotate the circle. This is rotate the framing. So rotate the framing. And this one is simple graspers. And there's infinitely many of them. So let me just draw an example. Okay, maybe here. This Z infinity is generated. Well, you can either, so let's say that this is my S1 direction in S1 cross S3. You can either draw, so yeah, I forgot to say, this C here, I want to be, the base point I want to be S1 cross a point here. Or S1 times little d3, this is my frame circle. So I'll take the red. So here is my base point, C. Okay, and here is a family of circles based at C. You take your finger. You want to go around the group element, so maybe you go You go up, right? You return from below. And then, well, I said, my simple graspers would tell me, it's a bit more complicated to draw, but it would tell me, like, take this sphere here, this is my meridian, you know, my S2 kind of, and do the twirling motion around this. So this is the simple grasper that I told you there. But actually, you can show that equivalently, this is generated by self-referential graspers. Self-referential is something that Dave Gabay introduced because they refer to themselves, really, instead of to C. So you draw like a sphere around here, like a meridian. So what I'm drawing here is I start with my finger, I travel all the way here, right? And now I want to go around the sphere that's meridian to this arc. You can just, you know, from looking from far, this is supported on an arc. You take a meridian of that arc. So both of these red pieces. And then you're going to do the twirling motion around this. So this is something called self-referential grasper. And sometimes it turns out, like, actually for circles, maybe always. Well, it depends on the base point, but you can just, instead of these, you can consider these. But yeah, the theorem says that everything is generated by this. Okay. Are there questions? Yeah, sorry, yes. Well, you can go k times. Yeah, forgot to say. Like here, you could go instead of once. Okay, here k is 1, right? But if z infinity here is generated by like elements, I don't know, t to the k, let's say. And I just drew the first guy in the family. The others would be, okay, I'll draw it. You go, you know, k times around this vector. And only then you come back and you do this. You go first k times around this one, and then you do this. Okay, now barbells. Barbells will give us diffeomorphisms instead of families of circles. But they are very much related to the graspers, as follows. Now in this model 4 ball, we will remove both U1 and U2. And that's going to be the model barbell. And note that grasper is just given by filling in, you know, U1. So we are going to use, yeah, let me say one more thing. So now we can draw two spheres that are meridian here and here. And this arc here that I'll call the bar. These are, this is together forms this barbell. And these are called cuffs, which brings me to what I should have said here. These were defined by Badny and Gabay in their paper, Knotted 3 balls. And this is their terminology. So this is the model barbell. Oh, yeah. Maybe they just call this barbell. And this blue is the skeleton of the barbell. Because what turns out is that if you think about this, well, think in dimension lower, okay? Maybe I draw it actually here. What we're doing in really low dimension, 2, right? So if this is D2, U1 and U2 would be points. And their neighborhoods would be little disks around. So we remove this. And the barbell is this pair of pens. And And but what is the skeleton of the barbell? Well, it's just the one complex to which this retracts, and this is pair of glasses. Okay? And then the grasper was like, fill this in, so there's actually this part was trivial sphere. So this is S1, S2, and this is the bar. And this is just the analog in dimension 4. Okay, so now I define the barbell map. The first thing I define is let BT be, it's going to be a map of G to itself. That's actually a diffeomorphism. And this is be an ambient isotopy extending U1T. Okay, so U1T up there was this one parameter family of arcs that moves. So just think of it as a path of arcs. And now the ambient isotopy extension theorem tells you that if you have some submanifold that move, you can actually lift that to diffeomorphism of the whole space. So this means, i.e., this is a one parameter family of diffeomorphisms. B0 is the identity on G, and BT of the initial arc U1 will be the arc at time t. And actually, it's also true for its tubular neighborhood. I mean, everything can be done with framings. So this is an ambient isotopy, and the important point is that when you lift this, basically what happens is that U1 moves, and then you're starting with the identity, so then you have to compensate for this movement. You have more and more of the ambient manifold also moving. And then when this comes back, although U1 came back, B1 is not the identity anymore. So the important point is that define the barbell map to be the time 1 of this. And then, so B1, okay? B1 is a diffeomorphism of G that satisfies this. So it means it sends U1 to U1 at time 1, which is just, again, our initial arc, okay? So this means that B1 can be restricted to the barbell, okay? Because B1 of U1 is U1. So you can just remove it. Let me show you in this dimension. So this is our toy example is dimension 2. What is U1T? What is the twirling isotopy? The analog of it is, well, okay, this guy is not there. We have this. And then we have this framed point that wants to move around the meridian of the other guy. So here is S1. And I want to foliate S1, which is the circle, by one parameter family of points. Because remember, what we did here was this guy moved around the one parameter family of arcs that foliate the sphere. And now it's going to be just foliated by points. Well, this just means take this and move it around this circle until it comes back. This is twirling isotopy in this dimension. You just take a little disk and move it around. So this is just something that lives in pi1 of embeddings of framed D0 in G, which is D2 minus a little D2. And it's non-trivial loop, obviously. And then you ambiently extend and look at the time 1 map. So what is this? Maybe you've seen it. And then you're going to restrict to the complement of this guy. So this is your barbell manifold. Actually, I need more space. So here is the description of the barbell map of BT. I will show you what it does on this meatball, which is also what Padnin Gabay explained. So if you draw, maybe I'll do another. Well, green was not used yet. Okay, so this is the meatball. This guy here is delta, called the meatball. Here it's a mid-arc, but it's going to be meatball there. And I'll show you the result of BT. I'll show you BT on delta, okay? First of all, B0 is the identity, so B0 of delta is delta. Then at 1/2 maybe, or maybe I want to do 3/4 of delta, I see this. This guy starts to push here, and then it comes to here. So the first time this disk wants to hit the green has to escape. So you have your finger that grows like this. And you just imagine, well, okay, I can draw it. So maybe this is epsilon. This is 1/2. 1/2 is this disk, which is now filled in, is here. Okay? And then you continue, and it has to hit here again. So you have to grow another finger that avoids that. So you're going to get here. And this is 3/4, let's say. And then this guy comes back where it was, and you get the following picture. This guy goes and catches here, comes back, but then goes another way. Okay, so this is B1 of delta, and now that I remove this is just the barbell map applied to delta. It's a new disk inside of the barbell manifold. And somehow completely analogously, you can study how this barbell map in dimension 4 acts on this midball here. So this is going to be the midball. And yeah, I don't have time to draw it, but you can try. And then maybe it gives you a clue why this diffeomorphism should be non-trivial. It really messes up this ball in the middle, right? The B of delta doesn't really look isotopic to delta. Are there questions? So analogously to what I did there for graspers, I defined this model, and in the model something happens, and then I want to plug it into the manifold. Now I want to do the same for the barbell map. So for a 4 manifold X, a barbell embedding is just the embedding of this barbell, okay? So it's just like some B that embeds the model barbell into X. And if X has boundary, this is away from the boundary. So just think of this as like this model is going to sit somewhere inside of our manifold, okay? And then we're going to use it to define a barbell diffeomorphism. So this is first and then second, the corresponding barbell diffeomorphism is defined as follows. So it's a diffeomorphism B, B, so it depends on the embedding. It's a diffeomorphism of X that's defined as B on the image of the barbell and identity otherwise. So identity on the complement. And now it might look complicated. How do you embed such a thing, right? But you should remember that similarly, like in the grasper situation, we just needed to choose basically the skeleton, which was like 2 points on the knot and an arc that connects them. And this was enough to say how one piece is going to move to another piece. Now it's actually enough also to choose the embedding of the blue. Okay, so I'll show you examples. maybe examples are here. So for example, or maybe I won't have space. Oh, I'll have to. Okay, example of a barbell embedding is this one. You take in S4 or D4, you take two unknotted spheres. And this is going to be your B of S2 and B of S1. And then you just need to choose a bar that connects them. So maybe it starts here, it goes to the other guy. It links it because spheres and circles link in dimension 4. So it's like a little hop link here in dimension 4. Then I link here, and then I come back here. So maybe now it's like this is called a theta barbell, I don't know. I mean, it has something to do with the theta graph and Watanabe's claspers. But yeah, I forgot to write this is in S4 or D4, but away from the boundary. And now what you just do is like you just say take a tubular neighborhood of this, and this gives you the barbell manifold. It's really just a thickening of this blue thing.
They have to be unknotted because
Well, it was easier for me to draw, but they don't have to be. No, for tubular neighborhood, it's just like you're thickening. You don't. The important thing is that you don't have to have like U1 and U2 that are, like now. I mean, you can just forget about U1 and U2. In fact, if you would just draw if you just draw this barbell in D4 that has unknotted spheres but a trivial bar, then the barbell map will trivially be isotopic to the identity, because I can just use now this BT, right? As soon as I can fill in this sphere by a ball, I get this isotopy there that will undo it. So you exactly don't want to have an unlink, like two disjoint cuffs with which bound three balls. This bar. The point is that the bar intersects the three ball again. And in fact, instead of D4, you can draw this picture in any 4 manifold. M4. Actually, sorry. Maybe I wanted this to be M for some reason. Because it's not exactly the same setting. So, and the 4 manifold, now we can think, okay, I can still choose some small unknotted 2 spheres in a 4 manifold. And now I want to choose a bar, but now I again have fundamental group choices. So I can do here, instead of just going straight, I can first do a loop alpha 1, and then here it's alpha 2, and then here alpha 3. And then what I'm actually saying is that you can read off a word. Starting from this point, you can read off a group alpha element to alpha 1. Then you're reading, here you're reading a meridian of the sphere, which is, say, y. So I have bar word. It's alpha 1, then y, then I do alpha 2, then I do x. So here a meridian may be called x. Everything should be oriented and so on. X, and then alpha 3. So if you have this, you determine the bar, okay? I mean, now this is enough. I mean, if you have unknotted spheres. Of course, you can also do knotted spheres, but like these are already complicated. Yeah?
Is it important that your spheres have a trivial framing?
Yes. Yeah. Yeah, trivially framed, yeah. Something I forgot to say is that this manifold is diffeomorphic to, similarly like that, you said it was S2 cross D2. This is S2 cross D2. Boundary connects some S2 cross D2. So yeah, so it is really just thickening of 2 things connected together. Okay. And one more thing I wanted to draw is another example, and this was this will come up later, is I want to draw another example of a barbell in a 4-manifold. I'll choose a sphere, S, and a circle C that just form the Hopf unlink in S4. So you could say S union C, this is just the Hopf link in S4. Okay? But then you have the manifold A, that's the complement of their tubular neighborhood. So if you remove a circle from S4, you get S2 cross D2, and then I remove S2 cross a point. So I get something that's diffeomorphic to S1 cross S2 cross interval. And I'm now working in the complement of the white, okay? Now in the complement of the white, I'm going to draw a barbell. And it's going to look like this. I'm actually going to take a non-trivial sphere, because this is a meridian of this circle, but circle is not there. So this is the S2 factor. So this is my S2. Then I'm going to do something non-trivial in the fundamental group, namely I'm going to go here k times around this. And then I'm going to go on another sphere, which might look strange, but again, looking from far, this looks like an arc, so it has a meridian sphere, and it's my sphere S1. Or maybe this one is S2, this one is S1. So I just gave you 2 spheres in my manifold, which is in the complement of the white, and a bar that connects them. And I'll call this barbell embedding BK. And I'll say something about it in a second. Okay. Bit short on time. Maybe this is going to be a bit quick, but to those who were here last week, it should make sense. So let me say number 3 is bridges between the 1 and 2. So I want to connect barbells and graspers. And I'll say a very useful fact that everyone should know. And that's that if you start with diffeomorphisms of a manifold X, maybe with real boundary, if it has boundary, you can evaluate any diffeomorphism on a given embedding. So if I have embeddings of some submanifold C, this just sends a diffeomorphism phi to phi composed with C, or little c. Okay, so fix a base point here, little c. So you have a fixed embedding of C into X. Now you post-compose with a diffeomorphism, you get another embedding, okay? And this map is a fibration. This here is a fibration. It's even a fiber bundle. That's a classical result, Palais. And let's determine the fiber. The fiber are all diffeomorphisms that, when evaluated on C, they give you back C. So fact is erased. So diffeomorphisms of X that fix neighborhood of C, well, that's the same as X minus this. Okay, so this now is a fibration sequence to which you can apply homotopy groups. So in particular, here you get pi1 of embeddings, of those embeddings again, going to pi 0, going to pi 0, going to pi 0. And the next guy will be pi1 of diffeomorphisms and so on. And why is this useful? Because of the following proposition. And that the connecting map here that I call M, so the connecting map of this exact sequence sends, well, if inside of embeddings I looked at my grasper families, then, okay, the connecting map M satisfies that amp of the one parameter family of circles given by Grasper, the simple Grasper family, is sent to the corresponding barbell. So it's going to be the barbell diffeomorphism where the barbell is obtained by restricting the Grasper to the barbell. Okay. So what I'm saying here is that this was true in these models, but it will also be true ambiently when you embed these things. Okay? And why is that? Well, that's because the connecting map in this exact sequence is the ambient isotopy extension map. It starts with a loop, lists it to a path of diffeomorphisms, and then restricts to the time 1. And this is the barbell map. Okay? Just a bit more space, because I have a part two of the proposition. Sorry, it's going to be on this side. So proposition number part 2 is that if you actually had C, which is isotopic into the boundary, then AMB is injective. So in particular, I mean, okay, I was not precise here. Like here I said you can take a general C, and you can really. Indeed, like all of this will apply. So maybe for this, I want for C is equal to circle, so that this makes sense. I define Graspers there. But you could also say C is an arc, and X is the Grasper manifold, and then you get exactly this situation. So for example, this shows that, yeah, I'll have to raise black. It's not very convenient. Are there questions? Okay. So let me state one theorem about bridges between barbells and Graspers. Well, this proposition already kind of relates them. Let me show you a concrete example, how they relate. So corollary of the proposition is the following theorem from our paper with Fernandez, Gay, Hartman, and myself this year, where we use this to conclude that if you start with pi1 of embeddings frame circles in S1 cross S3, S1 cross D3, based at S1 cross a point, then you can apply your AMP map. So ambiently extend your loop to a path of diffeomorphisms and take the time 1 of that path. You get into diffeomorphisms. Well, you take time 1, but similar like with barbells, you remove the thing on which your diffeomorphism is constant, right? It's like we removed U1 because it was preserved by B1. So here you would take S1 cross D3 minus the circle, and you will get S1 cross S2 cross interval. Okay, so this here is exactly S1 cross D3 minus the neighborhood of S1 cross a point. So we are exactly in the situation of that picture. And so the corollary says that this is injective. And inside of this, I showed you some examples. Well, when I was there, I talked maybe about S1 cross S3, but you can also just think of this as sitting inside of S1 cross D3. So you have those Graspers families there. So here you have these Graspers, maybe like a Z infinity, given by those T to the K Graspers for K's in Z. And now you know that they will inject here. And not only they inject, they exactly map to barbell maps. This here is, you get the diffeomorphism BBK for every K in Z. So in other words, you get a Z infinity in here. Okay, since I don't have much time, I'll finish with just one sentence about claspers. Another thing that I wanted to maybe say, but didn't have time, is that even before this story with Graspers and barbells appeared, Watanabe constructed certain diffeomorphisms of four manifolds and actually also of families of diffeomorphisms. So he constructed and showed that there are non-trivial classes in homotopy groups of diffeomorphisms of D4. But in particular, his construction works for pi 0. And this is a theta graph. For the theta graph, he can do a construction which is inspired by, again, by claspers. So let me just write that. I think it's claspers. And that Watanabe has Watanabe's claspers. For example, generate a Z infinity inside of pi 0 of diffeomorphisms of S1 cross S3. And they are all given by constructions involving this graph. But also Badin-Gabai used barbells like there to construct diffeomorphisms of S1 cross S3. And so one connection that I want to mention is that you can relate these constructions. You can show that Watanabe's claspers are obtained by something like this ambient isotopy extension map from Graspers, okay? And so both Graspers give both claspers of Watanabe and also barbells of Badin-Gabai. So that means that because both of these, both Watanabe and Badin-Gabai construct a Z infinity in here, using Graspers you can compare them and see that they're actually the same lists of diffeomorphisms. You just need to choose parameters correctly and you get exactly the same lists. Okay, thanks for the attention.